This is a 3 by 3 by 4 rectangular prism. Let me propose a game. Choose one of the vertices. From there, you are allowed to move only along segments that are tilted at 45 degrees with respect to the edges. In other words, along the diagonals of the square faces. For example, a first move could be this one. From there, you can continue on the same face or switch to an adjacent face. The goal is to reach the opposite vertex in 6 moves or fewer, where by move I mean each step from one edge to the next along these diagonals. Before you pause the video to think about it, let me tell you something. In this video, which took me several weeks to design, we will not only learn how to solve this specific problem, you will learn an algorithm to solve every problem. Okay, maybe that sounds like a bit of an exaggeration, but not that much. The algorithm I'm talking about is Dijkstra's shortest path algorithm, the one used to find the shortest route between two cities. Some of you may already know it. What you might not know is that it can be applied by hand, in a simple way, in many very different contexts. In the first part of the video, I will show you why it works and how to apply it manually using what I call the table of infinities, a simple but extremely powerful tool. In the second part, we will translate the algorithm into pseudocode and use Python to explore the solutions of some puzzles that you can later challenge your friends with. If you follow me step by step, I promise you will be satisfied with what you learn. Ready? Let's begin. The shortest path algorithm applies to graphs, that is, sets of points that may or may not be connected by edges. More precisely, it applies to weighted graphs, where each edge is assigned a value called weight. If we imagine the points as cities and the edges as roads, the weight can represent the length of the road, the travel time, or the cost of the trip. Regardless of the interpretation, the goal is always the same: to find a path from a starting point to a destination that minimizes the sum of the weights of the edges we travel along. Are we looking for the shortest path, for the fastest, for the cheapest, or the solution of a puzzle with the smallest number of moves? As you will soon see, this algorithm is extremely flexible and also surprisingly easy to apply. Let's look to a concrete example. We label the vertices of this graph and try to find the shortest path from A to H. At first glance, we might notice the path ABH with total weight 8. But is it really minimal? Looking more carefully, we can find AEGH, which has one more edge but total weight 7. And here, the fundamental question arises. When we find a path that seems to be the shortest, how can we be sure that there is not an even better one? That is exactly what the shortest path algorithm is designed to answer. To apply it in an organized way, we will use the table of infinities. To avoid making it look like magic, let me explain what this table actually does, using again the metaphor of cities. Imagine you're a tourist visiting the first city. Look at the cities directly connected and record their distances. If there is no direct road, write infinity. Once you have done that, mark this city as visited and move to one of the cities with the smallest value. When you arrive in a new city, look at the unvisited cities directly connected to it. Do you get a shorter route if you go through this new city? If yes, update the value with the new minimum distance. Otherwise, keep the value that is already there. After updating, mark this city as visited and move to the unvisited city with the smallest value. From there, look at the directly connected unvisited cities, and update their values if passing through your current city gives a shorter path. And the process continues in this way. Because of how the algorithm is constructed, the values written on the visited cities correspond to their true minimum distance from the original city. This is not yet guaranteed for the cities that have not been visited, since their values may still decrease during the process. When the destination city is finally marked as visited, we will have found the minimal path. As I said, there is a very practical and orderly way to carry this out: the table of infinities. It is not the official name, it is simply a name that helps with memorization, and it sounds cool. We prepare a table with one column for each vertex of the graph, from A to H. In the first row, we write infinity in every cell except in the column of the starting point, where we write 0. From now on, we repeat two alternating moves. The first is the vertical move. We take the smallest value in the current row, copy it into the cell below, and circle it. This becomes the reference value for the next row. In this case, the smallest value is 0, so we copy it below, circle it, and we eliminate the cells underneath in that column. The second is the horizontal move, which consists of completing the new row. How do we do that? The reference value in this row corresponds to the vertex A. For every other cell in the row, we write the sum of the distance from A through a direct edge and the reference value of the row, which in this case is 0. For example, in column B, we write 6, which is the weight of the edge AB plus the reference value 0. In column C, we write infinity, because there is no edge connecting A and C, and so on. In fact, this first row simply records the weights of the edges leaving A. Once the row is complete, we perform the vertical move. The smallest value in the row is 1, which appears in both column D and column E. We can choose either one, it does not matter. Let us choose D and make it the reference value for the next row. We eliminate the cells below in that column and proceed with the horizontal move. To complete this row, we insert in each cell the sum of the distance from D through a direct edge and the reference value of this row. For example, in column B, we write 5, which is the weight of edge DB equal to 4, plus the reference value 1. The cell in column C remains infinity, because there is no edge between D and C. In column E, we would normally write infinity, since there is no direct edge, but instead, we keep the value 1 that appears in the cell above. In fact, this is the final rule you need to remember: the values in each column can never increase, because they are tracking the shortest path from A. If the new value is larger than the one above, we simply keep the previous one. Let's continue. In column F, we write 3, which is the weight of the edge dF equals to 2, plus the reference value 1. The remaining cells are infinity, because D is not connected to G or H. At the end of the row, we perform the vertical move again. The next reference value is 1, corresponding to the vertex E. We copy it down, circle it, and eliminate the cells below. Then we perform the horizontal move. We look at the edges connected to E, add the reference value 1, and confirm the result only if it is not larger than the value in the cell above. Otherwise, we keep the previous value. Vertical move. We bring down the smallest value, which is 2, in column F. Horizontal move. We update the vertices directly connected to F. Vertical move. we bring down the tree in column C. Horizontal move, we update the vertices directly connected to C, and so on. We stop the procedure when the reference value corresponds to the destination vertex H. Notice that as we proceed, there are fewer and fewer calculations to perform because more and more cells are eliminated. When we finally reach H, the magic happens. Not only does the last reference value, in this case 6, correspond to the total weight of the shortest path, but we can also reconstruct the path itself. To find the path, we start from the last reference value, which is 6, and move upward as long as the cells contain the same value. When we reach the highest 6, we move along the row until we reach the reference value of that row, which in this case is 4. Then we move upward again along the 4s, and when they end, we move horizontally to the reference value of that row, which is 2, and so on until we reach the top. In practice, we move vertically along cells with the same value and horizontally to the reference value, alternating these moves until we reach the first row. The vertices corresponding to the reference values we pass through are A, E, F, B, and H. If you check the original graph, you will see that the path A, E, F, B, H has total weight 6, and it is indeed the shortest path. Amazing, right? This process can also be adapted to directed graphs, where edges can be traveled in only one direction, like one-way streets. I leave you an example here. If you pause the video, I'm sure you will understand how the procedure changes even without an explanation. For completeness, I should mention that the algorithm does not work with negative weights, but that situation does not occur in the most common applications. Now, let us go back to the initial puzzle. Did you find the solution? Personally, I found it only after applying the algorithm. First, I built a graph, whose vertices represent the reachable position along the faces of the rectangular prism. The edges of the graph connect only those positions between which the allowed move is possible. All these edges have weight 1, since each move counts as 1. At that point, I realized that the reachable points are 18 and the edges are 34, which is a bit too much to handle comfortably by hand with the table. Fortunately, the algorithm is easy to code. Here is how short it is in pseudocode. As input, we give the number of vertices and the weight matrix, where the entry EUV represents the weight of the edge between U and V, or infinity if no edge exists. We introduce a vector called row, which stores the current distances from the starting vertex, and a vector called visited, which keeps track of which vertices have already been selected as reference values. As long as the destination vertex has not been visited, we repeat the same two alternating moves. The vertical move consists of searching the smallest value in the row among the unvisited vertices. That vertex with index U is marked as visited. The horizontal move consists of updating the distances of the vertices adjacent to U that are still unvisited, replacing each value with the sum of the reference value and the weight of the edge UV, but only if this new value is not greater than the previous one. When the vertex n has been visited, the program returns row n, which is the minimum distance between vertex 1 and vertex n. The Python code I actually used also includes automatic reconstruction of the path and a check to avoid infinite loops in case no path exists between the two vertices. If you want to see the code and try it on other puzzles, you can find everything in the link in the description. In fact, you will find much more. A complete interdisciplinary study and game activity designed for high school class. If you're a teacher, you should definitely check it out. In any case, when I ran this code, bingo! The shortest path in the puzzle really exists, and it has 6 moves. And it is even easy to remember. You start by bouncing along the same 3x4 phase for the first moves, then you use the final move to switch phase and reach the opposite vertex. Boom! I have not checked whether it is the only solution with 6 moves. Let me know if you find another one. Using the same code, I also tried to solve other classic problems, such as the one made famous by the movie Die Hard with a Vengeance, where we have to measure exactly 4 gallons of water using only unmarked containers of 3 and 5 gallons. The allowed moves are filling the jug completely, pouring water from one jug into the other, or emptying the jug completely. The algorithm not only produced the known solution, but also confirmed that the shortest solution takes 6 moves. I do not know if it is clear by now, but with this algorithm, if you can identify the configurations of a puzzle as vertices and the allowed move as edges, you can solve the puzzle in the minimum number of moves. Many mathematical puzzles can be interpreted in this way. You will be able to solve them. In theory, even the Rubik's Cube could be treated like this. The problem is that the number of possible configurations is so enormous that the adjacency matrix would have about 10 to the 38 entries. This is not a theoretical limitation of the algorithm, it is a computational one. Take a look at the material in the description if you want to experiment with other puzzles or bring this activity into your classroom. And whatever happens in the meantime, don't panic.